All right, it looks like we're recording. And let me know if there's anything wrong with the slides. It looks like they're all right. I'm just a little paranoid. Here's where we left off last time. We've learned about dynamically allocated memory. We learned about structs, how to build a little, kind of the closest thing C is going to have to an object, at least that comes with the language. And then we started building stuff out of that. That was enough to let us build what we called linked structures instead of just storing stuff in arrays. We can organize our data structure using pointers, storing a little bit of it in different parts of memory. So we started with probably everybody's favorite first linked structure, a linked list. We wrote code to add stuff to a linked list. We had just finished talking about how to write code to destroy a linked list or to free all the memory associated with it. You'll remember first backing up, first we wrote a bad implementation of this that depended on a dangling pointer. It accessed memory we had already freed. And then at the very end of class, we made this version that worked. And it worked by, it went through and freed all the nodes in a linked list. There's the call to free right there. But before it did that, it took I think of it as taking a picture of the next node or getting a copy of the next pointer out of that node so that after I free it, I can still see what the next node was. And this particular version just keeps removing nodes from the front of the list until the list is empty. So, and there are other ways you could do this. This, to me, seemed like the most natural way to do it. We've got one more topic in the leftover material from talking about data structures that we can build using structs and mallocs, and malloc. And this topic is really about creative uses of pointers to make code simpler for things like this. This is something we can't really do in Java because even though Java references are a lot like pointers in C, you can do some things with pointers that you can't do with references in Java. In particular, and we've already done a little bit of this, you can take the address of a pointer and you can use that like the address of anything else. You can use that to both look at the value of that pointer and to change it. So if we're willing to write a little bit of code that uses pointers to pointers, we can simplify a lot of linked list code and code for a lot of other data structures. This is our first chance to take a look at this. We'll come back and look at it again a little bit later, but this is kind of a warm up to see how using pointers in C can let you get creative in how you manipulate some data structures. So we are going to write a little bit of code to remove a node from a linked list. And first we're going to start by looking at how you'd normally do that, maybe in a language like Java. And then we'll try to simplify that code using pointer to pointer, just to kind of fold some of the cases together. Our representation for our linked list is the same one we've been working with. I'll pretend that our linked list is going to be made out of this node structure on the left, same one we've been using. I've got a short name for it, node. And I've got a list structure on the right, and this represents the whole list. That's kind of so I can have a little data structure that I could pass around between functions, and that would be their way of getting access to the whole list. Like we said last time, all I've got in here is a head pointer right now. But if I wanted other fields to help me keep up with that list, I could just put them all in this struct. So first, let's talk about the standard way you probably would have removed a node from a linked list if you were doing it in a language like Java. And we can do the same thing in C. I'm going to write a function remove value. You give it the list struct, and you pass that by address. So its first parameter is you need to tell me where your list is in memory. Second parameter is what value do you want to remove? And then the function returns true or false if it's able to remove the node. And that just means if the value was on the list, it'll return true. If you ask me to remove a value that isn't even on the list, it'll return false. And the way we normally do this is we kind of think of it as two cases. If the node I'm looking for, if the value I'm looking for is in the first node, then to remove it, I need to change the head pointer to the list. And that's what I've kind of drawn down here. If you've got a linked list, And this list object contains a head pointer that points to the first node. And then, of course, each node points to the one after it using its next pointer. If you wanted to remove this 103 value, then that requires changing the head pointer. So we can handle that as a special case. That's what this little fragment of code does. It says, I've got a list, it's got a head pointer. If the list is non-empty, because I guess the list might have no nodes on it, in which case I better not try to look at the value on the first node. If there isn't even a first node, that would be dereferencing a null pointer. So first I check to make sure it has a head node, that the head pointer is non-null. And if that has the value I'm looking for, so look at the head pointer, look at what its value field says, and if that matches the value you're trying to remove, then remove that node. What's it take to remove a node? Well, I'm going to unlink it from the list, but I also have to free its memory. That's something you didn't have to worry about in Java. So before I unlink it, I take a copy of the node I want to remove, and I just put this in the node variable n. Then I unlink it. This says, if you let me point down here, it says take the head pointer and make it have a copy of the next pointer out of the node you're removing. I don't have a picture for this, but that takes this head pointer and it makes it point past this node down to this node that has a 9 in it. Now I've removed the node from the list. That's all it took to remove it, but I'm assuming the memory for that node was mallocked, so I better free it or no one's going to be able to free it. So I free that node and then I return true because I successfully removed it from the list. This is just the first half of this function, this kind of the special case of if the node you want to remove is the first thing on the list, here's what you have to do. Otherwise, if it's not the first thing on the list, then you remove it by changing the pointer out of its predecessor. Same kind of thing you probably did in Java. If it's the more general case, again, if it's not the first node on the list, we have to go find the node that comes before it. And that's what this little loop does. This first while loop here, it says, well, maybe the predecessor is the first node on the list. So we start out the predecessor, kind of like my picture shows, pointing to the first node on the list. And then we keep walking down the list. This pred, inside this while loop, this pred equals pred arrow next. Just like when we were traversing a list, that's moving us to the next node, or it's making pred point to the next node on the list. And while we're walking down the list, we check to see if we found the predecessor to the node we want to remove. So we first make sure, well, is there a node that comes after this predecessor? That's what this first condition says, is the next pointer out of the predecessor non-null, and that would mean it evaluates to true. And is it different from the value we're looking for? As long as it's different, we keep walking down the list. So we'll stop either when we hit the end of the list, there's no node after the predecessor, or the node after the predecessor has the value we're looking for. Either of those will get us out of this while loop. Once we get out of the while loop, we check and see, I think of this as checking to see why we got out of the while loop. If we fell off the end of the list, then there's nothing to remove. But if we stopped before we hit the end of the list, then it must be because we found the predecessor to the node we want to remove. And that's what this condition is doing. If there's something after the predecessor, if there's a node after the predecessor, you must have stopped because you found the predecessor or the node you wanted to remove. And then this code is almost the same as the case above. I take a copy of the node I'm removing because I need to free it. I unlink it from the list. So let's say we're removing this 9. This pred arrow next says take the next pointer out of the predecessor node and give it a copy, change it, so it points to whatever node came after the node you want to remove. So that takes this arrow and makes it point to this node with the 42 in it. And then we free the memory from the node we just unlinked. Again, if we didn't, that would be leaked memory. We return true because we successfully removed a node. And then on the way out, if none of that happened, then we didn't successfully remove a node. So this is how you might normally write it. And this is fine. I would say it's just maybe twice as long as it needs to be, because we're treating removing the first node as if it's a special case. Wouldn't it be simpler if we could just go find the node we want to remove and remove it, whether it's the first node or not? And that's what this implementation does. At least that's what it tries to do. This implementation doesn't work, but it's the idea that we're going to implement. And once we figure out how to do it, it's just going to take a small change to this to make it work. So let me quickly tell you what this implementation is trying to do, and then I'll tell you why it doesn't work, and then we'll fix it by, we'll fix it using a pointer-to-pointer technique. All right, so here's a remove value. It works just like the previous one, except it's about half as long. And like I said, this one doesn't actually work, but it's the idea we're going to make work. Here's what it tries to do, and I tried to illustrate this with pictures over on the right. Instead of looking, so I'll just write some traversal code that looks for the node I want to remove. It'll start out pointing at the first node. It'll walk down the list looking for a node that has the value you want to remove. Let's say we want to remove this 9 here as an example. I go look for a node that contains the 9, and that's what this first loop does. I start it, so target, like my picture shows, is the node I want to remove. So I just go look for it. Target starts out pointing at the first node, whatever the head pointer is. And as long as target is really pointing to a node, it's not the null pointer, and the value in that node is different from the value I'm looking for, I just keep marching down the list. Once I get out of this loop, if I found the node I'm looking for, then target should still be non-null. So same trick we were doing before. If target is non-null, I remove that node. Almost the same code that we were doing before. I take a picture of the target node. I make target point to the node after that one. I free that node and I return true. And like my picture shows, this doesn't actually work because this line right here, when I'm trying to remove the node from the list, I'm making target point to the node after the one I want to remove, but that doesn't really change the structure of the list. Target is just a variable I'm using to iterate over the list. So when I say, like, let's say here I find this picture here I find the node I want to remove, maybe this 9. When I do this assignment, I'm saying take target and make it point to this node with the 42 in it, like this bottom picture shows. To remove that node from the list, I got to change this pointer right here. It doesn't matter where target points. I need to change the next pointer out of a node. And in general, and I claim this is the thing we need to observe. In general, to remove a node from a list, you just have to change one pointer. And that's what we're talking about on this slide. We're going to fix this by, instead of keeping up with a pointer to the node we want to remove, we're going to keep up with a pointer to the pointer to that node. And like I started to say, anytime you remove a node from a linked list, at least if it's a singly linked list, that requires changing one pointer. If it's the first node on the list, then that pointer is the head pointer for the list. If it's some node in the middle of the list, that pointer is the next pointer inside a node. But either way, the pointer you need to change has the same type. Backing up, if you're removing the first node, you need to change the node pointer. That's the head of the list. You need to change the head variable, which has type pointer to node. If it's some node somewhere in the middle of the list or somewhere else in the list, you need to change the next pointer out of a node, but that's the same type. It's a pointer to a node. Instead of keeping up with, again, I already said this, but I'll say it again. Instead of keeping up with the node you're trying to remove, instead of keeping up with a pointer to the node, like let's say you're trying to remove this node with the 9 in it. Instead of keeping a direct pointer to that node, we're going to back up and we're going to keep the address of the pointer that points to that node. Said differently, we're going to keep up with the address of the pointer you have to change to remove that node. Our next bit of code, let me back up a couple of slides. This was the implementation that didn't work. We tried to find a pointer to the node we want to remove, and then the problem was we couldn't remove it just having a pointer to the node. Instead, I'm going to take the same variable target, but I'm going to change its type so that it points not directly to the node I want to remove, but to the pointer I need to change to remove that node. And here's what it takes to do that. If you kind of squint, this code is almost exactly the same as what we did before. I just changed the job of target. Like I said a moment ago, I kind of backed it up. So instead of pointing directly at the node, it holds the address of the pointer I need to change. Well, if target is holding the address of a pointer, its type is going to need to change. Instead of being a pointer to a node, I made it a pointer to a node. So now it holds the address of the pointer I might have to change to remove a particular node. When I start out, I think probably this picture shows it. When I start out, I want target to hold the address of the head pointer for the list. And then as I traverse the list, it's going to move down and next, say if the head pointer doesn't point to the node I want to remove, I'm going to step it ahead so that it points to the next pointer inside a node. I don't have a picture for this, but if I kept walking down the list, as target moves down the list, it's then going to point to the next pointer inside this 9 node, and then the next pointer inside this 42 node, until I either fall off the end of the list or I find a pointer that points to the node that has the value I want to remove. So, like I said a moment ago, I started out holding the address of the head pointer. I just take the head of the address pointer and I make target point to that. And then as long as there's a next node, as long as target points to a pointer that's non-null, so here's how I check it. Target is a pointer to a next pointer or a head pointer. So I dereference it to see if the thing it points to is non-null. As long as that's non-null and that pointer points to something different from the value I'm looking for. So I dereference target to get the pointer to the node I'm looking at. I look at the value field in that node, and as long as that's not the value I want, I move target ahead. We'll revisit this syntax. It's maybe a little bit tricky, but even at this point, I think you can understand it. I dereference target. So now I have a copy of a pointer to a node. I go get the next field out of that node. So this is moving target down the list. So I dereference target to get the pointer to the node I want. I go get its next field, and then I take the address of that. And that's my new value for target. And every time I do that, you can think of it as moving target down the list. And then I bail out of this loop either because I fell off the end of the list or I found the value I'm looking for. If I fell off the end of the list, then target would be pointing to a null pointer. If it's not, I must have found the node I was looking for. Same as before, I get a copy of a pointer to that node so I can free it later. And this line right here is probably the most important one. Like my picture shows down here, target is holding the address of a pointer. The pointer I need to change to remove a node. So like the picture shows, let's say I want to remove this 9 in the list. Target is pointing to the next pointer inside the node that comes before it. To remove this 9, I just need to change that pointer. So I dereference target. That lets me assign something to this pointer I've colored in red. I want to make it skip past this 9 node, so I assign it to whatever the next node after this 9 was. I take the pointer that target points to, that's this red thing. I go look at its value field, that's this, I don't think I colored this one, but that's this pointer down here, and I assign that to whatever target points to. That changes this pointer, so it points past this 9 node. And then I've removed 9 from the list. The list now goes straight from 103 to 42. The only thing left to do is free the memory for this 9 node. Fortunately, I took a copy of a pointer to that node before I removed it, so now I can free it, and then return true. You don't have to do your code this way, but if you compare, this code to remove a node is about half as long as the code we started with, the code that treated the head of the list as a special case. This is handy for things like linked lists. We'll see later for trees. This can even be more convenient because instead of just having one pointer out of every node, trees have typically a left and right pointer out of every node. This technique can let you fold a lot of those cases together and deal with them all at once. We'll revisit it, and in a couple of lectures, we'll look at similar code to simplify implementation of trees. And that gets us to the end of where we were supposed to be in our last lecture. I think we're catching up a little bit because we got that done in the first half hour. Any questions before we leave this? We talked about linked structures, we built a linked list, and then at the end, we used this pointer-to-pointer trick to simplify some of that code, something we couldn't have done in Java. Questions? All right. Our next lecture, I claim, is really important, especially as you start writing bigger programs and you start having to debug them. We've learned a little bit about debugging already. We learned how to use GDB early in the semester, I think day 3. And that used to, earlier when we were teaching this class, that used to come in much later. We decided it made sense to give students tools to see what's going on in their program early on. So we promoted that. But there's still a lot more that we can say about debugging. And this is other material that normally got presented about halfway through the semester, about where it is right now. We just moved the GDB topic a little bit earlier. We're going to talk about a few different tools that can help you debug your program. And then I think we'll have a little bit of extra time to start talking about bitwise operators. That's our topic for our next lecture, but our last topic for today will kind of lead us into that. So I've got 3 debugging techniques I want to talk about. The first one isn't really a tool. It's kind of a part of the C language. C has support for an assert statement. And it's the same idea as what you have in Java. Assert is a way of putting statements in your code that help you check the correctness of your program as it's running. And I'll try to sell you more on the idea of assert in a moment. I'll be saying many of the same things they probably said in Java, how you can think about assert and why you might want to use it. If you want to use assertions in C, there's a header file you have to include, assert.h. And then that lets you, much like you did in Java, it lets you put assertions in your code. And an assertion looks like this, assert. So if you include this header, you can put in statements that look like this, assert, and then inside parentheses, any condition you want to check. And then a semicolon. So you write this kind of like a function call or kind of like a statement in the language. The idea of assertions is they let you put checks in your program to see whether or not it's working correctly. Within your program, often you'll write code and kind of in your mind, you'll say, well, at this point in my program, here's what should be true. Kind of like when we were doing the linked list code, for example, I said in some places, well, at this point, this pointer better be pointing to a node that has the value we want to remove. And I tried to write my code so that I was true. I think it was correct, but that might be a good job for an assertion. You could put in an assertion to check that during execution. So whatever condition you put inside this assertion, the compiler will write out code to execute that condition. And if the condition is true, just like Java, if the condition is true, your program keeps running happily. If the condition is ever false, the compiler will write code to terminate your program. So if any assertion ever fails, you're going to know about it right away because it stops the execution of your program. I've got a slide that shows this. It's my next slide. The example down here shows if you called a function f, and maybe you took 2 integer parameters, and for the function to work correctly, maybe a better not be 0, and maybe b better be positive, just depending upon your function. You could put an assertion in your function to check that. It would look just like this, assert a better not be 0, and b better be positive. And with this assertion, if anyone ever called this function with values that didn't satisfy that condition, it would crash your program right away. You can put assertions in for anything that you want to check within your program. And I guess there are a couple of nice things about this. Everybody knows what assert means. So rather than just having an if statement with a printout, if someone saw an assert in your program, they know that that is a kind of a sanity check within your program. It's a way to make sure what you think should be happening in your program is really happening in your program. You can put, like my examples show up here, you can put in assertions for anything you want to check, like this this last one. If you're using a pointer and you want to make sure that pointer is non-null because of what you're about to do with it, you could put an assertion in for that. And then if you were wrong, the compiler, during execution, this would get caught right away. The nice thing about this is with assertions, you don't have to write out the code to print out what went wrong and where it went wrong. Whenever an assertion fails, your program, like I said, it will terminate and you'll automatically get output that looks kind of like what I'm showing down at the bottom. This will all be on one line. I just couldn't fit it all on one line on my slide, but it'll say something like assertion failed, and then it'll say the condition on the assertion, using exactly what code you put there. So it'll give you a human readable report of what went wrong, and it'll tell you where it failed. So you don't have to write your own statement to say, I'm checking this here, I'm checking this here. It'll give you a file and a line number where the assertion failed, so you can go back and check this within your program. I think the right way to think about assertions is they're kind of like comments within your program. They're kind of ways of saying, well, at this point, I believe this has to be true. At this point, I believe I've done this. But a comment just gets thrown away during compilation. An assertion gets checked during execution. So it is at least a way of saying what you believe about the execution of your program, but a way of saying it so during execution, it can get checked. So again, I think of these as kind of executable comments within your program. We already had an assertion. It's in one of our earlier examples, but I didn't talk about it in that example because we hadn't talked about assertion yet. But if you look back at our examples, especially our earliest examples of a resizable array, we probably had code that kind of looked like what I'm showing here. If we were about to put something in a resizable array, we might check to make sure we had room for that thing. And then if we didn't, we would increase the capacity of our array. Using realloc, we could easily make our array larger to hold that new larger capacity. And then we could store then once we had resized our array, if necessary, we could store that value in the next element of our array. I deleted this when we started writing our own code for this, but if you look back at the examples, I had an assert right there before I stored the value. And I think I tried to show off how you can use an assert. Whether I had to resize here or not, if I'm about to store a new item in the array, I better have enough capacity for it. So I wrote an assert that says, well, at this point, if you're about to store another item in the array, the number of items in your array better be less than the capacity. You better have some spare capacity. Otherwise, this assignment is not going to work. This assertion would be a way of testing the code that I wrote up here. If I made a mistake, increasing the size of my array, maybe if this condition was wrong or something, this assert would help me catch that. And it kind of matches what I said about executable comments. You can think of this assert as saying, at this point, you better have enough capacity, or I'm counting on this array having enough capacity to store at least one more line. At least one more item. And because it's an assert, this will get checked, and during execution, I'll know right away if this assertion failed. Just like in Java, a nice thing about assert is you can disable assertions if you don't want to use them. Assertions, because the compiler is writing code that checks every assertion in your program, it means if you use an assertion a lot, it's probably going to slow down your program maybe just by a little bit, depending upon where you use the assertion. If you just use a few of them in main, probably no big deal. But if you've got a loop that runs millions of executions and you call it all the time, an assert inside that loop is going to have a lot more overhead. So you can disable assertions. You could do the same thing in Java. Java just does it kind of backward compared to C. In Java, there's a flag you give to enable assertions if you want them checked. In C, there is a compile time flag that you can pass in that disables all assertions. So if you use assertions and you compile normally, the compiler will write code for all of those assertions. But if you put this flag, it's -d ndebug. It looks kind of weird, but we'll see later. The right way to read it is to think of this -d as a define. So -d says define this thing, and this ndebug that comes afterward, you can think of that as no debugging, or really it just means turn off assertions. So if you recompile all of your source files with this -d ndebug flag, all of your assertions get turned off, which if you were worried about the computational overhead of an assertion, this turns them all off in your code. So it makes it easy to turn on debugging code when you're developing. And then maybe when you release something and you don't want the performance overhead, without even changing your source code, you can go in and suppress all the assertions. That's all I've got to say about assert. We've got a couple more tools to talk about. Before we transition, any questions? So I encourage you to use assert in your own code, especially if you're worried about things like if you're writing code and you're worried that you might have an array out of bounds access. You could put an assert in and do your own bounds checking. You wouldn't necessarily have to do this everywhere, but usually there are places in your own code where you feel confident about indexing into an array. And there may be other places where you'd say, well, I think this is right, but I'm not sure. An assertion could help you catch a bug right away. And that makes sense because array out of bounds is the kind of thing where if you overwrite memory outside of your array, it may not crash your program right away, which can make that kind of error a lot harder to debug. An assertion to help you check that could make it a lot easier. So I said we're done with assert. We've got another tool to talk about, and this really is a software tool. This isn't part of the language, but there's a tool I haven't told you about yet. But now that we're using dynamically allocated memory, this tool is going to be really, really handy. Hopefully, you're going to get a lot of use out of this for the rest of the semester. The tool is called valgrind. I know it's written, it looks like valgrind, and it's fine if you want to pronounce it that way. But my daughters, who are into all things mythological, tell me, oh, this is the name of the gates of Valhalla. And that's pronounced valgrind. So as I understand it, this tool is supposed to be pronounced valgrind. What does it do? It is a runtime error detection tool, or I guess properly you would call it a dynamic analysis tool. Dynamic just means it works while your program is running. To use it, you run your program, and valgrind can watch what's happening as your program executes. And watch what's happening means it can make sure that, well, for certain things, your program isn't making certain mistakes. It can catch certain kinds of errors because it's watching every instruction, really every machine instruction that your program executes as it's running. How does it do this? Well, inside valgrind, it pretty much contains an emulator for whatever instruction set you're running on. So typically, you're probably running on Intel or I would have said x86 hardware in the past, AMD 64 type hardware. You're running a standard Intel style instruction set. And valgrind, at least if you're running on a machine like that, the valgrind that you can use knows that instruction set, and it can take every machine instruction in your program and it can simulate it. so that it can watch what's happening in that instruction. So it is really watching the executable code in your program by simulating it or emulating what every instruction does. Because of this, your program is going to run a lot slower inside valgrind, maybe 10 times. It's going to take 10 times as long to run, or even 100 times as long to run. For a program that's really compute intensive, this could be problematic because under valgrind, it might take so long to run that it's hard to use a tool like that. But typically, for the tiny little programs we're writing in this class, that's not going to be a problem. So valgrind watches what your program is doing as it's running. And as it emulates these instruction sets, there are certain things it can watch for. It's really got a number of built-in tools that it can use to detect certain kinds of errors. There are command line options for valgrind that let you tell it what tools to use. If you say, the syntax is a little weird here, it's dash dash. So a lot of programs are like that. By convention, if they have an option that's more than one letter, many programs will put 2 dashes in front of it instead of just 1. So dash dash tool equals memcheck says to valgrind, I want you to use your memory checking tools as you're running my program. You usually don't have to say that because memcheck is the default for valgrind, but you can say that, and I wanted to mention the tool. This enables the memcheck tool as you're running. What does the memcheck tool do? It mostly looks at heap allocated memory. Every time you allocate space for heap memory, it remembers where that space starts and ends. And then every time you access a memory address, either within that space or near it, it checks to see if it's inside that space. If it's not, so if you allocated a block of 40 bytes and you try to access memory that was just a little past that block or a little before that block, valgrind can catch that and give you an error message as your program runs, which effectively means it can catch out-of-bound accesses to dynamically allocated memory as long as you're just a little bit out of bounds on one side or the other. Since it's keeping up with all of the memory you dynamically allocate, at program termination, it can report any memory that you leaked. So if you allocated a bunch of blocks of memory and you never freed those, valgrind is keeping up with them. It can tell you that you never freed those blocks of memory, which is going to be pretty handy. It can even look for file leaks. I've got an option for that in a moment. When you report at program termination, it'll tell you if you leaked memory or not. If you include this extra option, dash dash leak dash check equals full, that'll give you what it calls a full leak report at the end. It'll tell you all the different blocks of memory you leaked, and like we'll see from an example, it'll tell you where you allocated each of those blocks so that you can think about where you should have freed them. It also looks for, and maybe this is one of its most useful things, it looks for use of uninitialized memory in any of your 3 big memory regions. So if you have a stack variable that you access and you never initialized it, it'll complain about that. Same thing with heap memory. Also with static memory, although I don't know if that would really show up since we know that static memory automatically gets initialized to 0. But this can be handy if you accidentally use a variable that you never initialized. There's a good chance valgrind can catch that. So I've said some things that valgrind can do, but I didn't say how you use it. That's what I talk about on this next slide. Kind of like GDB, valgrind expects to have access to the symbols defined in your program, all your variable names and function names and things like that. It'll still work without that, but it'll be able to give you a much more useful report if you put the -G flag on your compile line. So, and I've said this already, from this point on, I would definitely make sure you always use that flag because you never know when you're going to need to debug a program. And then the way you use valgrind is you put it in front of the program you want to run. So valgrind is a program. When you want to run it, you run on the command line. You put valgrind first, and then any options to valgrind. And that's what I'm talking about here. Like if you wanted to say, I want you to use the memcheck tool, or I want you to also check for leaks and report those at the end. Those are valgrind options, so they'd go right after the valgrind command. And then after that, the executable program you want to run. So whatever program you want to debug with valgrind, you put that next. And then if your program had any options, like command line arguments that you had to pass it, those come after your program. So the valgrind stuff, kind of like we've probably used the time command already, kind of like the time command, it goes in front of the program you want to run. So you're basically saying to valgrind, I want you to run this program with these options or checking for these kinds of things. So down at the bottom, I've got an example of how you might actually do this. If you had a program called program and you wanted to run it in valgrind, you might say, valgrind, I want you to run this program. And while you're running it, I want you to use the memcheck tool to look for out of bounds access to dynamically allocated arrays using uninitialized memory. And at the end, I want you to report any memory that leaked. To show off valgrind, I wrote a bad program here. It's not super complicated, but I made 3 arrays and I put them in different regions of memory. So up here, the static array, well, that's a global variable, so it's allocated in the static region of memory. It's got 10 elements. I made a 10-element array that's a local variable, so it's stack allocated. And then down here, I made a 10-element array that's allocated on the heap, and I keep a pointer to that. I wrote code that goes through each of these arrays and writes a 0 into every element. But I deliberately put a bug into each of these. If you look at the bounds on my loop, well, all of these loops go for I equals 0 up to and including 10. And you know that's wrong. If you've got a 10-element array, its indices are 0 through 9. So now this should have been a lesser than sign, or I should have stopped at 9 here. So all of these loops access an array out of bounds. And valgrind can help check this. So if I wrote this program and I compiled it with the -G flag, and here I called this program bounds. It should be posted on our example programs for today or posted with those. If you compile this with the -G flag and then you want to run it in valgrind, well, like I'm showing up here, you'll run valgrind, you'll tell it to use the memcheck tool, you'll tell it to report leaks when you're done, and then, in this case, the bounds program I want to run. The output from valgrind is going to look kind of like this. You'll get a report that says, hi, I'm valgrind, here's what I'm running. And then after that, if there are bugs in your program, if you access memory out of bounds, you'll get a report that looks like this. This number over here, that's just the process ID for the program I'm running. We don't really need that, but in operating systems class, we'll talk about things like that. So that's just identifying which program you're running. This report, I want to tell you what it says. This first line says, you tried to write to memory that you shouldn't. Invalid write of size 4. Well, that makes sense. If you back up and look at the code, I made an int array. So every element of the array is 4 bytes in size. And when I tried to assign to this element 1 past the end of the array, I was writing 4 bytes to memory, but it's memory I shouldn't have been writing to. It's off the end of this dynamically allocated array. And sure enough, that's what this report is for. If you look at this bounds line 22 in that example, backing up a slide, that's this line right here where I'm accidentally writing past the end of a heap allocated array. This tells me you wrote to memory, you write a 4-byte thing to memory that you shouldn't. Here's the line where you did it. And then the rest of this tells me where I allocated that block of memory. Since this is a dynamically allocated block of memory, there has to be a place where I allocated it. And this line right here, line 17 of main, backing up one more time, that's this line right here where I actually mallocked the block that I accidentally, or in this case on purpose, I wrote past the end of that block here. So the report valgrind gives you, you definitely want to be able to read this report and make sense of it. And right here, I'm telling you what the report means. So I'll expect you to know this and be able to use it on your homeworks and maybe on an exam if I ask you about this. Questions before we move on. So this is one example of the valgrind output. It reports some more stuff. You can see I've got a flat or a little thing at the end that says this report goes on. But if you run this yourself, you'll see it doesn't catch the out of bounds access on these other two arrays. Backing up, I've got a stack allocated array, I've got a statically allocated array, and valgrind, and here I write past the end of them. And valgrind doesn't catch that. Its memcheck tool is good for catching out of bounds access for dynamically allocated arrays, but not those other two types of arrays. It does, I mentioned it has a bunch of tools built in, and you can try different tools. There is an experimental tool that's available in valgrind that tries to catch errors in these other two types of memory. To use it, you, instead of using memcheck, you say -- tool equals exp -sg check. The way to remember that is, I said it's an experimental tool, so I would say it's probably not industrial strength right now. So this exp in front means it's experimental. And then the SG check, you can think of that as static and global. Or sorry, stack and global. And those are the two types of arrays that we're talking about. We had one stack allocated, one local array, and one global array. If you turn on this tool, it uses various tricks, various heuristics to try to catch out of bounds access to stack and global arrays, or stack and statically allocated arrays. I'm saying tries to here because, well, the way C programs are compiled, you can't always do this with perfect accuracy. But valgrind tries to use certain tricks to catch cases where you might be accessing an array out of bounds. And if you use this tool on the same program, so up here, let's say we had the same program, but instead of using memcheck, I say use this experimental stack and global check. Now it catches these other two errors. I left out some output from valgrind, but on this line, it's catching my access to my global array. Same as with the dynamically allocated array, it tells me where I accessed it out of bounds on line 25. It generally only gives one report for each error. So even if I access this out of bounds 1,000 times, I'm just going to get the report for the first time that happens. So just because you only get one report doesn't mean you only made, or only one error happened during execution. And this next block down here says you wrote 4 bytes past the end of a stack allocated array. You did that on line 28 of your code. And here's the array that you wrote. It was 40 bytes in size, 10 elements, and you wrote right past the end of it. So this tool, I will say your results might be mixed on it, but it's intended to help you check for errors on these other two regions of memory. Like I said, valgrind can catch a variety of errors. I quickly tried to review. Was there a question?
Yeah. Why did the error message say that it was 0 after expected? Shouldn't it be say like 4 after expected or something?
I can answer that. I feel more comfortable reading this answer because this is like this line, address, this is almost the same thing. Address blah, blah, blah is 0 bytes after a block of size 40. And here, even though the format is different, I think it's saying the same thing here. There, I would say it's talking about the starting address. So if your array, all these arrays are 40 bytes in size. They're all 10 integers and each integer is 4 bytes. So they're all 40 bytes in size. That's what it's saying right here. The 0 bytes after it means the start of the int you tried to write, the one that was out of bounds, was right past the end of the array. Even though you're right that the last byte of it, was further into memory, the starting address of the memory you tried to write to was right off the end. So that's how I read this 0. And like I showed a moment ago, you can see kind of the same thing happening here with 0 bytes after a block of size 40.
Okay, thank you.
No problem. So I was going to go through a catalog of errors that might get reported by valgrind. And same as before, I'll expect you to know what these mean. You'll be able to use them in debugging your own programs. And if I ask you a question on an exam, you should be able to make sense of valgrind output. So here, I allocate, same as before, I dynamically allocate a 10-element array, and then I write right past the start and the end of it. So this is just like what we saw before. It's a 10-element array, so it doesn't really have an index 10. Its last element is element 9. And here, well, you can index earlier into the array with an index of -1. That may seem silly, but the compiler can write code for that just fine. It's probably just not what you want to do in this case. Here, I'm getting a value out of memory. So when valgrind, since this is dynamically allocated, when valgrind catches this error, I'm going to get a report like this: invalid read of size 4. So you're trying to get something out of memory you shouldn't. It was a 4-byte thing. Here's the line of code where you did it. And same error we saw before. It was right past the end of your block. So 0 bytes past the end of a block of size 40. Here, instead of reading memory, I'm writing to it. And instead of writing past the end, I'm writing before the start. You can see now the error message says invalid write, because I'm trying to put something in memory near that array. And here I'm writing to an element before the array. So the starting address of what I'm writing is 4 bytes before the start of the array. I know these seem, here I'm writing right past the end, and here I'm writing right before the start, but the report is different because it's talking about the starting address. And here for this write, the starting address of where I'm trying to access memory is 4 bytes earlier, but here it's right past the end of the array. All right, so here I'm talking about reading and writing off the end of a dynamically allocated array. A common type of error, whether it's dynamically allocated or not, is to accidentally use memory that you never initialized. And that's what this program does. I malloc, same size, a 40-byte block of memory. And then I look at element 0 without ever putting anything into it. And I would say it's a bug to even ask, is element 0, does it have this value or not? Because if you never put anything in it, that's uninitialized memory. So who knows if it's going to have 0 or not? There's no point even checking that. Valgrind will report this, and its report will look like this. This is one that people often, they see this and they don't know what it means, which is why we're talking about it in class. You'll get a report that says conditional jump or move depends on an uninitialized value. That's because you got an if, and what your if does is based on this element of your list, but it's malloc memory, so who knows what it contains, so who knows which way this if is going to go. Even if you try to obscure it, here, instead of testing an element of list, I copied it to a variable, and then I tested that. Valgrind still catches this error of val has a value that's who knows what it's going to be, because I copied it from malloc memory that I never initialized. So who knows what that's going to be. So in both of these cases, you're going to get a report that looks like this. I notice this kind of report a lot when people are working with strings. Here, I'm just using an array of ints, and hopefully these two error messages make sense. Let's say you allocate a string and you never put a null terminator at the end. Let's say you fill in characters in a string, but you forget to put the null terminator at the end. And then you try to print that string, maybe calling printf. When printf tries to print it, it's going to print character after character, looking for the end of the string until it hits a null terminator. If you never actually put a null terminator there, you're going to get this same kind of error message. Because inside the code that's printing that string, it's going to keep looking for a null terminator. And once it gets to the end of the string, it's going to keep going through bytes of memory until it happens to hit a 0 in memory. Now, probably it'll eventually hit a 0, but if you never filled in characters past the end of the string, if you never put a null terminator there, then it'll start complaining like this once you start using parts of that array that you never put anything in. So This is an important kind of error to look for in valgrind output. I mentioned it can detect memory leaks. And if you use that tool, -- leak check equals full, you'll get a report at the end of your program of where you mallocked memory that you never freed. This will only happen at the end of execution because until your program terminates, who knows whether you're gonna free that memory or not. But here I allocate space for 100 bytes of memory, but then I let my program terminate without ever freeing that memory. If I tell valgrind to report on leaks, at the end, it'll give me an execution like this. You allocated 100 bytes in one big block that you never freed. So definitely lost means you didn't free it, and at this point, you're not gonna be able to free it. Here's where you called malloc. So it'll tell me the line of code where I allocated that block. It can't tell me where I should have freed that block. That's kind of up to me as the programmer. But it can at least say, oh yeah, you allocated it here. Maybe you need to think about your plan for where that's going to get freed. In the same sample program, I also open a file that I never close. So that's a file leak. And I don't think I've shown you this, I mentioned it. But if you give the flag -- track - FDs, that's saying check files that you open. And if you say equals yes on that, you'll also get a report at program termination of any files that you opened that you didn't close. For this program, it's actually going to say when your program terminated, you had 4 files open. Well, I only opened one of them, but remember your program gets standard in, standard out, standard error at startup for free, and you are not expected to close those. So at termination, if it says you've got those 3 streams open, there's nothing wrong with that. You're not expected to close those. But if it says something like this, you had 4 files open and exit, then that means you must have leaked at least 1 file. Here, I opened this file, but you can see in my code, I never closed it. And at termination, valgrind can catch that. And it says, oh, you had 4 open. And that means I must have had 1 extra open. It even tells me where I opened it. So it says you opened a file ABC. That's this one I opened up here. And you did it on line 12 of this program. And just like with leaked memory, hopefully that can help you go back and say, oh, here, where should I have closed that file? That's all I got to say about valgrind for now. But like I said, hopefully you'll get a lot of use out of that when we're grading your programs. Starting with project 4, we're going to start using valgrind to help catch errors in your program. And part of the grading will say, if you have memory errors or memory leaks or file leaks, it might cost you, I think it's up to 30% on your program. But this is your countermeasure against losing those points. You can always check your program with valgrind yourself and fix errors like that. Questions before we move on to our next tool? All right, valgrind, we saw a bunch of things you can do with it, and it supports different kinds of error checking. I said it's a dynamic analysis tool because you have to run a program to use valgrind. It watches what happens as your program is running. And that's a nice way to try to detect errors, but it can't detect errors that don't actually happen when your program is running. Let's say you've got a potential buffer overflow, but it doesn't actually happen when you test your program. Valgrind isn't going to be able to catch errors that don't actually occur. Maybe it could occur on certain inputs, but maybe when you test your program, you don't happen to give it any of those inputs. So dynamic analysis is great for detecting errors, but they have to be errors that actually occur when something goes wrong. Static analysis is another approach, and it doesn't depend on running your program. It depends on just looking at your program and using a big pile of heuristics, typically using a bunch of heuristics, looking for things that might go wrong in your program. Its static analysis tools have kind of been built with a bunch of rules that say things like, if you see code that looks like this, and then you see code that looks like this, it's an error. This is the kind of thing that can go wrong. Or this is something that could go wrong during execution. There are a variety of static analysis tools. One of them called cppcheck is readily available. It's available on Linux machines. It's free. It may not be industrial strength, but it's at least one we can try out. If we take the same error program, and this is the one that made 3 arrays of 10 elements each, and then it proceeded to access every one of those arrays out of bounds. Without even compiling your program, cppcheck can look at this code and look for these kinds of errors. Again, it's a static analysis tool, so it doesn't need a compiled version of your program. It needs the source code for your program. So you can run it like this, cppcheck, and then as an argument, you give it the source file or source files you want it to look at. Looking at the files, cppcheck gives you a report of any errors it catches, and you can see, at least for this simple program, it catches all 3 of our errors. It says you got an array, static array, and on line 25, you access it out of bounds. You've got a stack allocated array with 10 elements, and on line 28, you access it out of bounds. This is all the code inside those for loops. And even for the heap allocated one, you've got a heap allocated array with 10 elements, at least based on how you malloc it. And on line 22, you access it out of bounds. So at least for a simple program like this, I'm impressed that static analysis can catch all 3 of these errors without even running our program. It can't catch everything. Programs can do some awfully tricky things, and no fixed set of rules can catch everything that could go wrong. If we take our program and we make it a little trickier, this is basically the same program. I've got 3 10-element arrays allocated just like before, but instead of putting for loops right here after I made the arrays, I delegate that to a function. So I call a function zerofill that does the same thing. You give it a pointer to the start of any array. It'll go through that array, initializing 11 elements. So for all these arrays, that's going to be an out of bounds access for that last element. I fill in every element with 0, and this is enough. This little bit of obfuscation is enough to keep cppcheck from catching this. If you run it now on this slightly trickier program, it doesn't catch any of these errors. This doesn't mean it's bad. I'm delighted to have tools that'll catch any errors in my programs. It's just for sufficiently tricky code, the static analysis is not going to be able to catch everything. But using a combination of static analysis and dynamic analysis tools, you're kind of building up a set of techniques that have better and better chances of catching errors in your code. If I was writing a program for this class, I would run it through static analysis tools like cppcheck to see if they can catch any quick to fix errors. And I would definitely run it through valgrind using some of the options we talked about to see if during execution, even if the program seems to run successfully, is there anything going wrong during execution that I can fix? That's all I've got to say about debugging for today. We've got one more topic. It's kind of a build up to our next lecture, so we'll see how far we can get on that. Any questions before we move on? All right, our one more topic is really setting us up to talk about bitwise operators. In C and in Java, although you didn't use this stuff in Java, there are operators for working not with whole values, not with all of an integer value, but just working with the individual bits in a value like an integer. Normally, if you make a variable of type int, you expect to use it as a number. You're going to use it to store a number. You're going to do math with it. But C and Java will let you go in and mess with the individual bits in that integer. On a common platform system, an int has 32 bits. And if you want, you can go in and look at and change each of those bits individually. And for some applications, you need to be able to do that. For cryptographic applications or compression applications, they depend a lot on being able to access the underlying bitwise representation for a value. So we're going to warm up to the idea of thinking about that, of being able to work with things, looking at and working with their individual bits. And to get ready to do this, it's going to be handy to think about numbers represented in different bases. Normally, we write down in our source code, we write down numbers in base 10, like normal humans do. But you already know, in C and in Java, if you want to, you can write down numbers in two different bases, in base 8, which we call octal, and in base 16, which we call hexadecimal. Why these two particular bases? Well, they make it easy to write down binary numbers, to write down particular patterns of ones and zeros, but to do it with less space. If you wrote down a number in binary, if you wrote down a 32-bit number in binary with ones and zeros, that would take, it'd take a big part of a line of code. In base 8, in octal, you can think of every digit of octal, every I want to say digit, although that's for base 10, every part of an octal number represents 3 bits. So an octal value is like writing down a binary number 3 bits at a time. Hexadecimal is even more parsimonious. Every symbol in a hexadecimal number represents 4 bits. So you can think of these as compressed ways or shorthand ways of writing down binary numbers. Now, you may already know how to think about hexadecimal numbers or to think about octal numbers. Just in case you don't, I'll remind you of this, or I'll cover it real fast. And if you're already familiar with this, then we'll say this is a reminder of how this works. Let's do octal first. So octal is a way of writing down numbers in base 8. In an octal number, every symbol, like I said, it represents 3 bits. Whereas in base 10, every digit can have a value 0 through 9. In base 8, every symbol we write down can just have a value of 0 through 7. So every symbol in an octal number, every digit we write down can only range from 0 to 7. Every digit has 8 possibilities. And that's how it represents 3 bits per symbol. If I've got 8 different symbols I can write down, then those 8 different possibilities can represent 3 bits. 2 to the 3rd is the number of different things I can do with 3 bits. 2 to the 3rd is 8. So that's why octal has 8 different things that can show up in each different position, 8 different symbols. Like it says on my slide, to write down an octal number, we'll use 0 through 7. We'll use just some of the decimal digits. An octal number might look something like this, 5174, and by convention, if you wanted to make it clear, oh, that's in octal, we can put a subscript at the end that shows the base. So this subscript 8 says that's a number in base 8. For an octal number, every position is worth 8 times the next position. I said that badly. Let me try again. If this was a base 10 number, then you would say, well, this 4 is in the ones place. This 7 is in the tens place. So whatever that 7 is worth 10 times as much as this 4. This 1 is in the hundreds place. So anything in this position is worth 100 times as much as what's in the ones place. And this 5 would be in the thousands place. So whatever's there is worth 1,000 times as much as what's in the ones place. Octal's the same way, except as we move up to higher place values in the number, we multiply by 8 instead of by 10. So this 4 is still in the ones place, but whatever's in this next position is worth 8 times as much. So like it shows in these bubbles, you could say, well, this 4 is in the ones place, so it's worth 4. It's worth 4, or more generally, it's worth 4 times 8 to the 0. 8 to the 0 is just 1. So that's like saying, yeah, this 4 is in the ones place. It's worth 4. This 7 is worth 8 times as much. So whatever's in this position, since we're in base 8, it's worth 8 times as much as the ones place. Continuing, this next position is worth 8 times 8 as much, or 8 squared times as much as the ones place. So this position is worth 64 times as much. And this position is worth 8 cubed times as much, which I think is 512. I'd have to check my math on that. So this number, 5,100 or 5178, this 4 is worth 4 times 8 to the 0, or just 4. This 7 is worth 7 times 8 to the first. This 1 is worth 1 times 8 squared, 8 to the second. This 5 is worth 5 times 8 cubed. And if we had more place values, we would just keep going in the same way. If we had another digit here, it would be worth whatever that is times 8 to the fourth. So just describing what this number means in base 8 gives us a way of converting from octal to decimal. You just have to do what we just said. If you took this number and said, well, that 5 is worth 5 times 8 cubed, the next 1 is worth 1 times 8 squared, the 7 is worth 7 times 8 to the fourth, and the 4 is worth 4 times 8 to the 0, you could multiply those out and add it all up. And if you did that in base 10, it would show you that, well, this octal number is equivalent to, in base 10, 2,684. So I claim just understanding the meaning of an octal number gives us a way of converting it to decimal. And I'm showing that over here in this bubble. Octal is for base 8. Hexadecimal is exactly the same idea, just in base 16. Well, if we're in base 16, it means for every position in the number, for every place value, I have to be able to write down 16 different symbols. I don't have enough decimal digits to do that, so I'll use all 10 of my decimal digits, and then I still need 6 more symbols to write down a number in base 16. So I'll start using letters. For a hexadecimal value, I'll use A to represent 10, a value worth 10. I'll use B to mean 11. I'll use C to mean 12, D to mean 13, E to mean 14, and F to mean 15. I wrote these down in a little table up here, but obviously you don't have to really remember that. Once you've counted up 0 to 9 for a particular position, you can start counting with the letters continuing on. So A comes after 9, it's worth 10. B comes after that, it's worth 11. So you just go through the first 6 letters after you get to 9. Same as with octal. Hexadecimal is the same idea, but as you move up in place values, each position is worth 10 times, sorry, worth 16 times the position to its right. I want to say the position that comes before it, but like all numbers, we're working our way right to left. So every position is worth 16 times the position before it. So this 9 is in the ones place, so you can think of that as being worth 9 times 16 to the 0, or 9 times 1. This E is worth 16 times as much. Well, looking at our table, E is just another word for 14 in hexadecimal. So this E is worth 14 times 16 to the first. B in hexadecimal is just another word for 11. So this B here is worth 11 times 16 squared. And this 5 up here is worth 16 times as much as the position before it. So this 5 is worth 5 times 16 cubed. Just like we did with octal, if you wanted to convert, sorry, yeah, I said that right, just like we did with octal. If you wanted to convert this hexadecimal number into base 10, you could do what we just said. It's worth 5 times 16 cubed plus, well, B is 11, so 11 times 16 squared, plus E is 14, so 14 times 16 to the first, and then 9 times 1, 9 times 16 to the 0. So on these 2 slides, here for octal and here for hexadecimal, I claim that I kind of defined what those bases mean, and probably already knew that. and I showed you how to convert them back to human, back to base 10. But that's not really what these bases are for. It's still good to be able to do the conversion, but like I said at the start, these bases are really for making it easy to work with binary numbers. And that's what we're going to do next. Hexadecimal or octal should make it really easy to write down a binary number, but to do it in the shorthand, so it doesn't take a huge amount of ones and zeros. That's what we're going to do next, but we're out of time, so we're going to have to save that for the end, or sorry, for the start of next lecture. Thanks for your attention. I'll go ahead and stop the recording, and if people want to hang around and ask questions, I'll be happy to take those.